In this topic, we are going to learn about vectors on the coordinates plane. The coordinates P can be defined as a position vector OP equals to column vector XY. We have an example here of coordinates P to be 6, 5. And the origin is 0, 0. And therefore, the position vector OP here can be written as column vector 6, 5. Whereby 6 is the horizontal distance away from the origin and 5 is the vertical distance away from the origin. Given this, the magnitude of position vector OP will be equals to, once again using Pythagoras theorem, square root of 6 square plus 5 square, which is equals to 7.81 units rounded off to 3 significant figures. In summary, coordinates P can be defined as the vector OP, and it can be written in this column vectors form. The magnitude of vector OP is equals to the square root of x squared plus y squared, because the vector OP here will form a right angle triangle whereby the horizontal length here is x and the vertical length here is y. Given column vector A and B here, we are asked to find the magnitude of 2a minus 3b. First, let's find out what is 2a minus 3b. It is equals to 2 times the column vector A minus 3 times the column vector B, whereby 2 and 3 here are scalar, and we can multiply the scalar into the column vectors. So we will have 2 times 4 minus 3 times 1, and for the y we will have 2 times 7 minus 3 times 5, which will give us column vector 5, negative 1. To find the magnitude of 2a minus 3b, we will use Pythagoras theorem, square root of x squared plus y squared. And it will give us square root of 5 squared plus negative 1 squared, which is equals to 5.10 units rounded off to 3 significant figures. In the grid below, we are asked to draw vector AB, which is equals to the column vector 5, 3. We will start from the points A, and the 5 here means that we will move 5 units to the right from A, and we will move 3 units up. And this will give us AB equals to the column vector 5, 3. Next, we are asked to draw the vector CD. Here we will start at point C, and we will move 5 units to the left because of the negative, and we will move 3 units upwards to give us the points D, and we will have vector CD. To draw vector EF, we will start from a point E. We will move 5 units to the right, followed by 3 units downwards. And this will give us vector EF. Once again, the x here for the column vectors will be the horizontal distance, and the y here for the column vectors will be the vertical distance. Next, we are asked to draw the vector GH. We will start from the point G. Because of the negative, we will move 5 units to the left, followed by 3 units downwards. And this will give us vector GH. Now, if two vectors are parallel, then they are scalar multiple of each other. In terms of column vectors, if these two column vectors are parallel, vector OP will be equals to k times vector OQ, and hence column vector x1, y1 will be equals to k times column vector x2, y2. Let's look at an example here. If vector P is equals to 9, 6, and it is parallel to vector R, which is equals to M4, we are asked to find the value of M. Since they are parallel, these two vectors are scalar multiple of each other, and we will have 9, 6 is equals to k times M4. Next, we will multiply in the scalar to give us 96 is equals to mk for k. Let's compare the y value here. Now, since these two are equal, we will have 4k equals to 6. Dividing 4 on both sides, we will have k equals to 1.5. Comparing the x value here, 9 is equals to mk. We will substitute the value of k equals to 1.5 here, and we will have 9 equals to 1.5 m. Dividing 1.5 on both sides, we will find the value of m to be 6. In summary, if two vectors written as column vectors here are parallel, then the column vector x1, y1 will be equals to k times x2, y2, whereby k is a scalar. And that's all for this topic.